As we mentioned before, when you do a free body diagram, 3, 2, 1, go. As we mentioned before, when you have a free body diagram, or in many cases you have a macro scale system, meaning that you're going to have millimeters and you're going to have meters, or inches to feet, like a football, like a baseball, like a car, like an airplane. When it's hundreds of millimeters, it's many meters, many feet. When you have systems like that, it's very important to have, first of all, before I forget, they're called macro scale, because macro scale, because micro scale, macro versus micro without I, because micro scale is in micrometers and up going to nanometers, because you also have nanoscale. Nanoscale is obviously nanometers. Okay, but before we go further, I wanted to clarify that in nanoscale and Armstrongs, you probably want to use something like quantum physics. But in macro scale, where you have millimeters and meters and feet and inches, the laws of dynamics, the mechanical laws of Newton, are very useful. So it's fundamental. It is very important to know where the center of mass is located. And if it's a square, it's very simple, it's right at the middle. If it's a cube, it's still pretty simple, it's still at the middle. If it's a sphere, etc. But if it's not a non-regular geometry, like I don't know, like a cloud or like an airplane, then we learned tools in statics to compute the integral of the surface in the volume to get the proper center of mass, because it's very important to compute the center of mass so that you can compute all your mass times acceleration and forces. Let's see an example. So let's say we have a system where let's say we have a bulldozer. I'm trying to see how to draw a bulldozer. Actually, doesn't look like it would be pretty simple. Let's see a bulldozer. Well, I want you to assume that what I'm drawing here is a bulldozer. Okay. All right. Then this is obviously the huge tire that he has, another huge tire. It could be a dump truck or anything. Really, what I want is to have a way to show you how to compute the center of mass. And actually, I think there are many examples like this in your statics books. So try to see if you can look at those examples. I think there's another mechanism that connects those like that, and another mechanism that connects those like this. Nothing, something like that. Okay, so and obviously this is going to have some type of load, like some rocks or something, or dirt, and they're asking us to compute the center of a mass, right? Where's the center of mass? And in this case, this is extended, and there's a huge load here. And this system obviously is different than if it's just the bulldozer with no extension and no load. So the center of mass is computed as we saw in statics by deciphering what are the forces. So again, the free body diagram. So they're asking us for the center of mass, and let's say we're gonna have some important distances. So we're gonna have this axis right here at the center of one wheel and another one right here, and let's say we have another one right here. The next question is where we're gonna choose our coordinate system. And remember that in dynamic, every time that you have a vector such as forces or electric field, it's completely important. It's very important. It's fundamental to find. It's completely necessary to find coordinate system. So let's say our coordinate system is going to be right here. My coordinate system X and Y. All right, and they're asking us to find the center of mass. And then the center of mass is somewhere. We have to find it. And it's going to be the mass times the gravity. So we know the gravity, and we need to know the mass. And if we actually need to solve this in a real world application, we can actually find two scales. That's why you have those type of scales on the road for trucks, to weigh them. And here you're gonna see that we're gonna have a force up here and a force up here, and the center of mass, and then some force up here. Okay, so if we were to say that in Z we have no forces, so summation of forces in Z equals mass times the acceleration in Z. This is 0, so nothing really. This is an XY, a two-dimensional problem. We can cancel this dimension right now. So again, as we said, we go from R3 to R2, and then simplifies quite a bit, because instead of dealing with system of equations that is going to have time x, y, and z, now we're gonna have time x and y. So at least we're getting rid of one extra equation. Okay, and our force vector went from I, J, K to I, J. So it's getting easier, right? At least we're getting rid of one dimension. All right, but then let's see what happens in X. Well, in X is not moving, so actually we're not gonna get too far by looking at X. But in Y, summation of forces, external forces plus summation of forces, internal forces, equals to mass times acceleration. So internal forces, again, right now we're not studying the stress or the deformation of the structure, which you'll do later when you look, if you go for mechanical engineering or or civil engineering, or even aeronautics, aerospace. But those things are not going to be studied right now. So we're going to only look at the bodies out, the forces outside. This is because of gravity. This is an external force. So summation of external forces equals to the mass times acceleration. Well, in X we said is 0, and actually we said we were going to do it in Y, and I didn't follow through. So Y it's not moving up or down. So what we have is, just like in statics, summation of forces in X and Y. So summation of forces equals 0. What forces do we have? We have that this is because of scale 1, we're reading a weight 1, a second weight. So the weight of scale 1 plus the weight scale 2 minus the load, or how to call that? Let's say the amount of material times gravity, material MT, rocks, whatever, which that we can know in advance. We can also weigh that. Minus M for the center of mass of the whole structure. Center of mass of the whole structure is going to be actually, we have two options here. We can treat this as an extra load. So this is just going to be a force because of this material, right? M times G. So let's just put it so we don't get confused. All right, minus mg. All right, cool. So in that case, we can know this force. We can measure this weight as well by itself before we pick it up. Say before we pick it up, we know exactly we're lifting 500 pounds or whatever. So this is known. This is known. We're actually using a scale, a sensor, a load cell, whatever, to know those values. This is known, and we are trying to know where this is located at. Okay, so if we go ahead and check our equation, we're gonna have that mg is equal to W1 plus W2 minus F, okay? Or, well, yeah, that's basically our equation. Or, yeah, we can just, if we want to divide by G because it's a constant, it's fine. But this is basically one equation. We can know this, that, and the force by just measuring our loads. But the unknown is, where is this located at? What is this distance? Or what is that distance to here? What is that distance? This is the question. Where is the center of mass? Right? So let's say up to here we have L1, and let's say that up to here we have L2. All right, so we're going to remove this because we have no information in Y. So let's say up to here we have L2. Okay, so what is the distance between your origin, which really my coordinate system should be right at the origin right here. I apologize for that. So this is my coordinate system right here, X, Y, my origin. And what is this distance? Okay, what is that distance? Lx. If you remember statics, we can use another equation, which is the moment. Okay, so summation of moments around the origin is equal to 0. And in this case, in statics, we always said it was equal to 0. But actually, in dynamics, it could be not equal to 0. It's going to be equal to the inertia times the angular acceleration. Okay, we'll talk about this later, but there's no angular acceleration, so it's going to be equal to 0. Just like in Y, there's no acceleration, so it's equal to 0. And that's why we're going back to statics. So that will be, if you remember statics, this force is right across the origin, so it doesn't count. But these two forces do count. So we have, we're going to say that counterclockwise is positive. So W1 times L plus L1 plus W2 times L2 minus mg times Lx. Obviously, all the lengths can be measured, and all the lengths are known, and all the weights can be measured and known. This is equal to 0. So see how simple this is? This is a number, that is a number, this is a number. And actually, if you didn't have that scale or the sensors, you can actually go ahead and do that W1 L1 plus W2 L2 minus W1 plus W2 minus F times Lx is equal to 0. Okay, so if you can measure your length, once you're engineering something, you can use sensors and experiments. So this is enough to actually measure something, test something, and find what is your center of mass with respect to x. Okay, which is the important case in this. In this case, really the important center of mass is in x, because you want to know if when this is completely loaded, this is going to tip over, right? That is the important case. And actually, to be more precise, if the engine is back here, you can actually add the weight of the engine too, because the engine is heavy. And if you noticed, there are blocks of steel at the back to compensate for those scenarios where you have load completely extended. So you can also add that. And W1 and W2 will completely take care of your forces, because they're scales that you're weighing, right? Anyway, so if you didn't have any scales, then you can use mathematically the expression to find Lx, right? You bring it to the other side and divide everything, and you can find your Lx. So this example is just to show that if this system was moving, you can first find the static time. What is the steady state? Steady state This means when time equals 0. No, sorry. This means, well, steady state means when it's not changing in time. It's not when time is equal to 0. It's when no variations, when changes with respect to time are 0. So there's no change. It's our equilibrium. That's another word. Equilibrium. So in steady state, whenever if at some point you need to quantify things because of the accelerations or the forces, first you can say what is the case when I have a trivial solution where my acceleration is 0. Well, that is very important, because then I can know what is the centroid, the center of mass of my system. Then from that, I might have to use that later on for acceleration computations, because all my forces are going to be around this center of mass. And we'll look at the examples later on where you need the center of mass for your system to be able to compute your accelerations.